The purpose of this lab is to experimentally calculate the n value and the magnetic moment mu of the bar magnet we were given, as well as the model of the experiment using glow script. Prior to the lab, we were given our mu value to be 0.5, which is based on the strength of the magnet we were given. The higher the mu, the stronger the magnet. And we can derive our n value from our equation for the magnetic field due to the magnetic dipole, which we can tell is proportional to 1 over n cubed, or 1 over r cubed, giving our n value to be -3. The result of our lab will be our n and mu values, as well as the net magnetic field at a 45-degree angle with reference to distance d. First, in our experiment, we'll determine the location of the magnetometer chip. Next, we'll find the specified distance for respective magnetic field measurement. And lastly, we'll calculate the 45-degree magnetic field due to distance d while taking into account the magnetic field of the Earth, so we can correct our Bayer values to get a correct magnetic field in the end. When looking at the physics involved in our experiment, the main parts we have are the magnetic field and the Biot-Savart law. A magnetic field is a region around a magnetic material or moving electric charge within which the force of a magnetism acts. The Biot-Savart law is an equation describing our magnetic field generated by a constant electric current. In the Biot-Savart law equation for a magnetic dipole, you can see I've highlighted which parts represent K in the equation to show how I'd solve for it. For our calculations, given that our y-intercept is equivalent to the natural log of k, and k is equal to mu naught over 4 pi times 2 mu, we can solve for mu, and we got mu to be 0.518377505, and given that our slope is equal to n, we get n to be -3.678. For the net magnetic field at a distance of d at a 45-degree angle calculated experimentally, we obtained a value of 6.16009 times 10 to the -5 teslas. For the net magnetic field at a distance of d at a 45-degree angle calculated computationally, we got 6.65038 times 10 to the -6 teslas. As we can see, our results for the net magnetic field at a 45-degree angle at distance d are different, and it's important to note that our computational calculated value of the net magnetic field doesn't take into account the z value of the magnetic field, while the experimentally calculated value does. Once we got our results for n and mu, we got the percent error for these results. For mu, we got our percent error to be 0.3676601%, and for n, we got our percent error to be 22.6%. Some potential sources of error are that the location of the magnetometer chip isn't exactly where it thought it was, or where we measured it to be, and there could also be interference from other metal devices nearby, as well as eyeball error. Eyeball error is the margin of error we take into account when we are eyeballing our measurement or looking at it, because we have to think about how our eyes aren't exactly perfect, so we could be off by a certain amount. Here I have my three-dimensional computer model on the left, and on the right I have drawn a two-dimensional, more simplistic model to make sense of the three-dimensional model. The light blue arrows in both models represent the magnetic field perpendicular to the axis. We can see how the blue arrows are roughly half the size of our orange arrows, and this is because the orange arrows represents the on-axis magnetic field. The on-axis magnetic field equation is mu naught over 4 pi times 2 mu over r cubed. The perpendicular magnetic field equation is mu naught over 4 pi times mu over r cubed. As we can see, the difference between these two equations is that the perpendicular equation is that it's half the value of the on-axis equation, so this is why the arrows reflect this in the diagrams. The green arrows drawn represent the magnetic field at various observation locations. In the diagram on the right, the direction of the magnetic field is indicated by gray arrows, and I have drawn green arrows where they are in the three-dimensional model to demonstrate their meaning. The magnetic field indicated by the gray arrows runs in the direction it does because the dipole moment of a bar magnet runs from south to north. If we hadn't oriented our experiment to compensate for the magnetic north and instead laid our meter stick at some intermediate angle with respect to the Earth's magnetic field, there would be additional external magnetic fields present as a result we would obtain a value far from the expected value. If we were to stick two identical magnets together end to end and rerun the experiment, I expect the magnetic field to be double, as our mu value would double, and because the strength of the magnet is in general represented by mu, the whole magnetic field would double. In conclusion, our mu value is 0.518377505 and our n value is negative 3.678. We also use GlowScript along with our computer code for GlowScript to calculate the 45-degree net magnetic field, and we also calculated this with our experimental data. We were successfully able to experimentally calculate n value as well as the magnetic dipole moment mu of the bar magnet we were given, as well as the model experiment successfully using GlowScript. Thank you.